so what did we do so far? So we discussed a couple of techniques, like started with diagrammatic perturbation theory, and then discussed how to, based on the intuition gauge from diagrammatic perturbation theory, one can derive an effective field theory for a given problem. So always the guidance is in a way one wants to understand some aspects of some model, so one has an idea what one wants to look for. Like example was the free energy of the weakly interacting electron gas. So in the first step, what we did was a diagrammatic analysis to figure out what are the building blocks which are the most relevant that appear in the diagrammatic technique. And then after that intuition is gained, one can actually, based on this, try to derive an effective theory now in the relevant degree of freedom. So we did this program called weakly interacting electron gas, where then the effective field theory, this is a 5-step program, involved one point, which is, so the first step is always doing the Hubbard-Satonovich transformation to introduce a new degree of freedom, and then one does the mean field analysis. And in the specific case of the weakly interacting electron gas, we found that the mean field equations are solved by trivial solution. And this is like what we said is nothing else but saying that the non-interacting ground state is stable against interaction and is right reference point to the perturbation theory. So now we want here to go through exactly the same steps, which are like generic steps for a different problem, where we will find that the mean field actually does not always have to be trivial, but there exist non-trivial solutions which are then an indicator for a phase transition. So the example that we are going to study is again electrons, just weakly interacting electrons. Now we want to take like what we found from the first problem. We started out from the Coulomb interaction. We saw that due to the presence of, a finite density of electrons, one has a dielectric medium, so the interaction is screened. So what we start out here from is now interacting electrons with a short range potential, actually an on-site potential. So where, in a way, you can say, well, that's already taking account the screening. Okay, and what we want to see that in this system, so you have a metallic system, you have freely moving electrons, they are not localized, they're like metallic state. And what we will see is that the interaction can there also give rise to a more interesting phenomenon, which is related to the stone instability and signals that there is a transition to a magnetic phase. So that's like magnetism in an itinerant, like a mobile electron metallic electron system. So that's the example that we are going to discuss. And again, so the program will be the same. First, what we are going to do is to look at some diagrammatic expansion of a certain correlation function, which is now chosen such that one can already see that something interesting is happening. But the idea is again the same. We do perturbation theory to see like what physically is going on, try to identify relevant diagrams, see what's physically going on. Once we have the intuition from diagrammatics, and in the second part of the lecture, so that's probably what we're going to do today, is the diagrammatic analysis. And then in the second part, with the intuition of the diagrammatics that we gained, we'll derive an effective theory. Then this will be for magnetism in the network. Okay, so that's the idea. And so we are going to find something interesting, which is an instability, the stone instability, and which is going to be a signal of this transition to a magnetic phase, which then will be analyzed like more systematically by the effective field theory. But we first start out with diagrammatics. Okay, so let me just say, so what we did so far we developed effective theory did is we derived an effective theory in terms of what we can call addressed photon field. So the effective field describes the interaction between the electrons. Addressed here means that the effective theory, where one integrates out the electrons, then gives rise to some self-energy of the photons. Okay, so these become massive, and this just reflects the screening going on in the metal. So that's what we did so far, and what this was based on was the observation that diagrammatics can be organized in terms of these ring diagrams or loop diagrams or bubble diagrams, which amount to the RPA approximation, or taking these diagrams. And we saw that in the field theory approach, one can then go systematically beyond the RPA by then considering like higher order terms in the field which describe interactions between the photons. Okay? So now, what we are going to see is that in the same system, the interactions, like again, interacting electron gas, can also have a more striking effect. So in a way, what we saw here is the electrons, what they did is exactly the screening of the charge. So that was the only effect, let's say, the more striking effect here is meant that the interactions also can make something more drastically with, let's say, the electron liquid, namely can cause transition into a new phase. And the transition is called the Stoner transition, and the new phase you'll see is a metallic phase. And technically, this then differs is like here, nothing really drastically happened with the electron gas, meaning in a way that the mean field was trivial. Okay, so the non-interacting reference state is the right reference state. Here we'll find that for the effective theory, there's non-trivial solution of the mean field equation, meaning that one has a phase transition and the non-interacting reference state is not right, doesn't have to be the right reference state, but interactions change the ground state of the reference state, which the preparation here should be formulated. Now, there's more interesting to this example that we are going, something more interesting that we are going to discuss now, but this will be only once we come, like probably next semester, if we continue, we'll discuss normalization groups and so on, like the phase transition, and then we'll see, revisit this example here, which is interesting in itself because this is now describing an interesting example of a phase transition which can happen at zero temperature. So a phase transition which can be tuned only by an external parameter. And this is so-called quantum phase transition, okay? And this then leads, like for loops around the fluctuations around let's say the transition point, one has quantum critical fluctuations and so on. It's all an interesting physics there. So this is an example. We'll discuss this probably next semester for like quantum criticality. Okay, so normally probably what you learned so far is normal phase transition driven by temperature, at finite temperature, but there's also like zero temperature phase transition driven by an external parameter, where then the transition is not driven by thermal but by quantum fluctuations. And this is a paradigmatic like example for this kind of quantum phase transition. So that's why this is also an interesting example to discuss. So let's say later. So that's not what we are going to do here. So what we want to do is first understand what is going on, then derive an effective theory. And once one has all the machinery of renormalization group, one can revisit the effective theory and analyze like the quantitative data of the effective theory. So later this is an example for quantum phase transition. So I don't know if you know the concept, so I don't write it down, but I just restate. So quantum phase transition at t equals 0, driven by some external parameter that is g. Okay? Okay, so that's why we are going to discuss this example first. It's like a more interesting example for this program, but later on there's also some more rich feelings. So what we are going to do is we start out from, again, a Hamiltonian of freely moving electrons that interact by, however, now some screened interaction. So what we start out is a little bit a different model, but the lower energy part is actually the same as we considered before. So we start out from some lattice Hamiltonian here for simplicity. For electrons which are now interacting not by a long-range Coulomb interaction, but interacting by a local or on-site interaction. And this is motivated because we saw that there's screening going on if one has a finite electron density. So instead of starting from the Coulomb potential, taking into account screening, we directly start out from some model where the interaction is screened, and therefore short range, or very short range on-site. And this is also called the Hubbard model, I think. Like in the first lecture where we discussed some typical examples of models that are discussed in condensed matter, I already mentioned the Hubbard model. Okay, so we have a Hamiltonian that consists of two parts. There's a free part and an interaction part, which is traditionally labeled as HU, where U is the interaction strength. Okay, this is just like how it's normally in the literature. So we have a free part of the Hamiltonian, which due to translation invariance is diagonalized, in this case by Bloch waves for the lattice. So we have here just some kinetic energy term, and then we have the interaction term, which is now of the following form. So we have an interaction parameter U. Then this is now counting I from 1 to n, which labels the sides of the lattice. And then because we have a local interaction term, well, due to Pauli principle, you cannot have a local term for the same kind of spin. Okay, so the interaction, if it's local, only allows, due to the Pauli principle, interaction between spin up and spin down densities. Okay, so it's just Pauli principle. Okay, it's clear, or yeah, it's clear. Yeah. So what you can have in mind is some kind of, let's say, d-dimensional lattice where you have hopping, which gives rise to some dispersion. Again, it's a translation invariant system, like it's a lattice, so one can diagonalize this by Bloch waves. This is like the momentum, and this is then an interaction between different spins and outside interaction. So you pay price U for having double occupancy of the sides. Okay. So E from 1 to n are lattice sides of some two-dimensional system, let's say. And epsilon p then of course depends on the exact lattice, but the dispersion epsilon p and dimensionality you can leave so far, for the moment just unspecified. Later on we'll specify some when we want to do real calculations, but now let's keep this just unspecified. For the moment. And then, oh, it's one. And then the other comment is that, well, this ni sigma is just the number operator, no? So sigma I is the side I, so it's the number operator on side I for spin sigma. Number operator for spin sigma on side I. Okay. So that's the model that we are going to discuss, and as said, so it's actually just a different model, but the lower energy physics is not much different from what the one we discussed so far. So in the end, the dispersion will not be so relevant. I mean, the dimension of course is relevant, but then the screen interaction, I mean, is just already takes into account the screening that we discussed before in the example. Okay? So, well, then what's the first thing that we do? Well, we have here the Hamiltonian, so let's like turn on our machinery. So the first thing is we go to a field theory representation, or to a path integral representation for the let's say partition function. So let's just for simplicity here write down the field integral for the partition function. I mean, in the end, one can introduce sources to derive correlation functions, but for simplicity, let's just look again at the partition function first. Okay. So we can derive, or we can just look at the partition function, which is again field integral weighted by the action, and the action now here. Okay, so this is just the free part again, this is the interaction part, just now all done again in Fourier transform tools. So the P here is again the form momentum, okay, so it's a d-dimensional momentum, and the Max-Barra frequency, and here just we go the local interaction term in terms of, I mean, the Fourier basis, so there's some factor due to the Fourier transform, and then due to momentum conservation one has three momenta, so I just wrote it in a very democratic way. Okay, so didn't introduce any small q, but then here's delta function for momentum conservation plus the local term. Okay, so this is the field theory.
Os dois com barra são trocados, senão os dois com se barra, eles são trocados.
Esses aqui?
Não, esse e o P1 e o P2.
Certo. P1 que...
Por que não seria o não barra?
O não barra assim?
É.
Oh, poderia também escrever assim. Na verdade, isso
Você está escolhendo desse jeito.
Isso não... o que seria, se eu pego esse aqui, esse hamiltoniano é a density. Aí seria que S estaria a esse lado, tá? Agora você vê que para transferir S aqui, eu vou pegar um menos e mais um menos. Então é um plus, tá? Então seria a mesma forma, eu poderia da mesma forma escrever isso de P1A, P2A, escrevi agora só para ter alguns instrumentos. P2 down, P3 down, né? Que seria a forma como está escrito aqui. Eu só escrevi dessa forma porque na construção do path integral a gente usa o normal ordering. Se você lembra que você na construção quer ter todos os creations em um lado e annulations no outro lado, mas no final não faz diferença, tá? Mas o sinal sim é importante, mas o sinal é mesmo como estava antes. Então não, boa pergunta, assim, né? Porque, mas tem a arbitrariedade aí. Só escolhi porque, na verdade, a gente também escreveu dessa forma nos exploit actions, porque isso é a forma que sai quando você bota a máquina aqui. Mas o importante aqui realmente é porque temos uma interação local, só tem essas combinações de spin, né? Spin up e spin down, das densidades diferentes. Não tem, então, Pauli principal, tudo com spin up, tudo com spin down. Então, isso foi o primeiro passo de escrever simplesmente o path integral. Agora a gente pode introduzir os objetos que a gente sempre introduz. Assim, tem a Green's function, non-integrating Green's function, que seria, esse termo a gente chama de as-int, so this is the integrating part of the action, this is the non-integrating part of the action. The non-integrating part of the interaction has here the propagator, so we can write down the free propagator of the system, which is normally called G0 or G0 of P, and just once more to point this out. So this is like again 4 momentum representation, Matsubara frequency, and d-dimensional momentum. And this diagrammatically we represent again by the line. And here this is now given by I omega n minus epsilon p plus me, and then this, if you want to do the momentum representation, this is diagram. Okay. It's actually the same propagator we had before also, only that now this dispersion we didn't do that by open so far. Okay, so this is the free propagator, and then we have the interaction part, which again we can draw in a similar way we did before. So now this is weighted by factor u, and we have here spin conservation, and here we have minus sigma, and then we have, well, I don't put in the momentum, but we have P1, P2, P3, P4, and all momentum conservation. Okay, this is the interaction part. Okay. All right. So, I mean, this is all what we always do, no? I mean, now what we always do, we use field integral approach, so we write this down. Actually, I didn't mention this on the exercise sheet on the first, where you should do the Matsubara summations for the harmonic oscillator. They also said, like, of course, you will need to know what is the expectation value of two of those. And the idea, I didn't write it down, but was, well, first you should write down the path integral, and then you can represent this in terms of I mean, the path integral expectation value, and this gives rise to 1 over the propagator, no? Or it's just the propagator, 1 of whatever is in the quadratic action. So on the harmonic oscillator problem, you don't have any degree of freedom apart from the Matsubara sum, so the propagator will be just I omega n plus omega 0 minus v. Okay, so this is like what we always do first, and now I'll just introduce some correlation function that I introduce, of course, with some insight. I mean, if you look at the problem, first you don't know what can be interesting, so I'll already introduce a correlation function which has to do with magnetization. And there we will find interesting physics going on. Of course, I mean, this is always a process, like, it's a process like, you can, I mean, someone has to have an idea that there can be some, like, magnetism going on in this problem, so this is why it's interesting to look at the correlation function that I'll introduce now, okay? So this is, there's some experience behind that from other, I mean, people. It has a story, of course, history, of course. But let me just mention one thing. So what we did so far was we considered interactions in the density channel, where these were coupled and these were coupled, like to 1 degree of freedom, okay? So, and the density channel gave rise to all, well, an effective, like, photon propagator, which is stressed by the interactions, and where the screening is like taken into account. Now here we already start from some effective model where we have the screening already put in because we have short-range interaction. So we don't expect any interesting physics going on like in the pure charge channel, okay? But then we said like, well, there's, or the density channel, we said there's 3 interesting channels in principle. So there was one which is related to superconductivity, so here might be that there's some superconductivity going on, but let's just, I mean, I'm just trying to motivate. So the density channel, we shouldn't expect any more interesting going on because we already like are considering here like screening of the interaction. I'm simplifying it because there's still like possibility of charge density waves and so on. So there's still also something interesting in the charge channel that can be going on, but this is a different story. Maybe you look at this. But if we are not considering the charge channel and don't concentrate on superconductivity, there's still the exchange channel. Okay, and the exchange channel somehow knows about spin. Okay, if we do like take the charge channel, we have here like this coupled to a degree of freedom, which is then not anymore like resolving spin, because like in the long range interaction there would be a sum over spin here, which is just like the charge. No, we said like the charge was well, said P plus Q, and then it's charge of Q. I mean, already summed over both spin channels, so there was nothing interesting anymore going on. So here we can now already think like, okay, if we are not concentrating on the charge channel, let's concentrate, not interested in superconductivity, so let's see what the exchange channel actually can get, okay? And this knows about the spin structure, okay? So that's motivation. Why now? You first introduce spin operators, then write down the correlation function that we are going to look at. So we introduce a spin operator for the k component of spin. R, I'll call it X, I don't know, let's call it R. No, here it's actually I. It's I. Okay, so this is here the case Pauli matrix. Okay, so this is the normal way how you introduce the spin operator. Okay, so this would be for k being x, y, or z. Okay, so the x, y, and z component of spin operator. That's known, no? I mean, if not, I can. No, that might be so this is S operator k component I. Sum over sigma, sigma prime, spin up, spin down. So that's the sum over spins. And then it's creation annihilation operator at both side I. And then they have sigma and sigma prime. And what is sum over sigma, sigma prime? And here's the sigma, sigma prime matrix element of the case Pauli matrix. That's no? Yeah. Okay. So this is let's let's say the case component in real space. Now what we often want to do is we want to look at the Fourier component, which then is 1 over n p plus q sigma k, which is fully transformed. So that's the k component of the operator. And then what it's often convenient to do, instead of consider like the z, the x and the y component of this operator, is to introduce the raising and the lowering operator, which is 1/2 okay, so this is just the raising and the lowering operator. So if you insert this in here, the sigma x plus minus sigma y, I sigma y, is a matrix which has here 1, like this would be 1 and this would be the other one. So one can see that this, if you multiply this with the two components vector, so this would correspond to flipping a spin from down to up and up to down. Yeah, that's why it's called raising and the lowering operator. Okay, but it's just convenient operators. So I assume that all this is known, no? Yeah? Or if not, I mean, just ask. So the Pauli matrices are known. So having introduced the spin operators and having tried to hand waving, say that, well, should be interesting maybe to look into some kind of magnetism here or an exchange channel, which can lift to magnetism. Let us introduce correlation function, susceptibility, that we want to study diagrammatically. So susceptibilities in general, so they are 4-point correlation functions, so they involve 2 creation and 2 emulation operators, so 4 operators typically. And susceptibilities are always like in a way a good indicator for phase transitions. No? If there's something divergent there, this is a good indicator for phase transitions. Okay, so I just introduce here the transverse spin susceptibility, and then I'll say some words on it. So as said, it's a 4-point correlation function. So far, let me think, we have discussed diagrammatically, we have discussed like the Green's function, which is a 2-point correlation function, which involves like creation and annihilation of an electron. We have discussed diagrammatics for the free energy. But what we here want to discuss, like diagrammatics for, or diagrammatic evaluation of a 4-point correlation function, which involves 4 operators. So let's introduce the object this depends on imaginary time and the distance between sides I and j. So this is the absolute value between I and j. And this is defined as following way. Okay, so this is already the expectation value in imaginary time now. Feeling to go. Okay, so what you do is, let's say you have your lattice. Say for simplicity it's a line. And what you say is, let's flip the spin of the electron at side I at some moment 0, and let's see what the reaction is at some distant point j at time tau to this flip. Okay, so let's say we flip here, spin from up to down. Let's see what happens here, if there's a response at this side. Okay, of course, if you don't have any magnetism, any magnetic correlations in the system, then it should be just trivial. There shouldn't be anything happening. So what we think is that if there's some magnetic correlations going on, this should be captured in this kind of correlation function. Let's do something at the system there, and let's see at a distant point how the reaction is. So if there are spin correlations in the system, this should somehow know about it. Okay? Now there's one thing that we haven't really discussed so far, but I try to motivate, and which what one can also make all more formal, and this is we're considering here. So I wrote down here the operators in now here, this is already based on the function integral representation. This depends on the imaginary time, so it's an imaginary time correlation function. Now we didn't really discuss the meaning of this imaginary time correlation functions, and I mean there's some which you can analytically continue to correlation functions that are typically appearing in response and so on. But just, I mean, think of it as I said, there's you're studying some correlation in imaginary time. Don't worry too much about imaginary time, so when you make this all formally, there's some kind of analytical continuation behind it, or just think of it that this is going to describe the system. Okay, so maybe next semester, if we continue, we can also comment more on the imaginary time correlation functions. But just take it as this idea. Change something in system at time 0, and then we look at the response at a later time. Okay? So this is what we first want to understand diagrammatically. But then this is written in real space and imaginary time, and the free propagators diagonal momentum space, so it's more convenient if you translate this first to the Fourier basis and write this down explicitly using the electrons, electron fields. So the Fourier transform, then this depends on the Matsubara frequency, the two-dimensional momentum Q. There's some convention for the factor here. And then we have here double sum over 4 momenta. And well, we just have to do the Fourier transform of this, which is already given here. So we will have here 2 momenta and 1 Q, which is the one. So this here corresponds to a spin flip. So you destroy one with the spin down and create one with spin up. So this is the raising operator. And this is like if you do the sum over k and the sum over q e to the iq rj, then this is the j component of this one here. Okay, so it's the Fourier transform, and then we do the same for this operator here, which now is the lowering operator. So k prime plus q down and k prime spin up. Okay, so there it's the opposite. You destroy one with spin up, create a spin down, so the spin flip in the opposite direction. Then, well, Fourier transform of this will. This is the q is the omega n is the Fourier component of the Tij. That's where we did the Fourier transform, and then what you end up is this 2 free summations. Okay, so that's the object that we're interested in, and let's just also represent this diagrammatically. So we can represent this starting from here. Now we destroy an electron, k prime spin up, create one with k prime plus q, spin down and so on, and just write the 4-point correlation function diagrammatically. Wait. K prime up, k prime plus q down, and here in going out, going k plus q down, Okay. Oh, actually, I didn't do this one, no? I said English came. Okay. So that's the representation. Let's write here equal like for the diagrammatic representation of the things that we're interested in. Okay? So that's the object that we want to understand, because we think that if there is magnetically something interesting going on, this should be captured in this function. Okay? Questions, or is this like clear, the diagrammatic code, everything? Yeah? Okay. So then what we want to do is we want to calculate this now using perturbation T, you know? So that's what we do. Take the non-impacting state as a reference state and try to develop an understanding of this correlation function. Okay? Let's see how that goes. So what we do is we do perturbative expansion in the interaction, okay? So we can immediately write down like the zeros order in the interaction, which is then, well, just connect these two lines, okay? Just spin up and spin down. Now the free, maybe I should write it down here, the free propagator conserves spin. So that's why we can only take this combination here. Okay? So now, if you look at the first interaction term, we can build up diagrams from this, inserting one of these diagrams. Okay? So there can be again those where we connect these and then connect these, and then we can insert this into here. But if you recall, we have a link cluster theorem for the correlation functions. And this was that they are all vacuum diagrams are cancelled. And actually it was not so clear what is the difference between a vacuum diagram and the connected diagram if you look at the Green's function, because they're the same, but I said, well, there's a difference if you look at higher order correlation functions. So the vacuum diagrams are those where there's no, it's a diagram where there's a diagram containing only the interaction, not connected to external legs. Okay? So we have now the possibility to look at the diagram where this is inserted into this, and then there would be a diagram where we take this, here the connected lines and this isolated. But this of course would then be a vacuum diagram. Okay? So you see, for example, this is not really connected, but it's not a vacuum diagram. Okay? So if we take into account only the diagram that survives according to the Laplace theorem, well, it's inserting this in here, and this can be only done, putting this in here, connecting then the spin in the right direction. So this would be the diagram first order, okay? Which is now weighted with a minus u, because we have e to the minus interaction. And this goes over. Second order is more interesting. Again, what we want to have is the non-vacuum diagrams, which means we have to insert the both of the interaction lines into this external X. Now there can be, again, different kind of diagrams, but now the point is that you can use again the same argument as we did for the previous example, that we will only take those diagrams which give the largest phase space volume. So these are the diagrams which have one free momentum summation per interaction vertex. Okay? So you could consider like a diagram of this type, for example, in second order, but you will see that a diagram of this type will always be in favor because of the free momentum summation. Okay? So I leave this to explore to you, but I'll just mention this, and it's the same argument we used before. If you use a kind of phase space argument, you will see that there's a certain class of diagrams which again will dominate due to phase space arguments. So in first order we didn't have to do anything, but higher orders, what we do is, again, we look only at the leading contribution from diagrams, we retain only those diagrams with one free momentum sum summation per interaction. And I leave this to explore to you. I mean, the arguments are the same as before, but if you only take again those where you really have one free summation for each interaction vertex, what you will find out is that you come to the ladder structure of diagrams. It's the so-called ladder diagrams. Or the ladder diagram series, which means that in second order you will have this, then in third order you will have this, and so on. Okay, so you form the ladders without any crossings, because the crossings will give restrictions to the momentum summations. Okay, here you always have in here one just free, completely free summation. Okay. So the statement here is just very similar to the problem before. One can again use phase space arguments to identify a certain class of diagrams which are the most important. And this here are not the bubble diagrams, but are the so-called ladder diagrams. Okay. And again, so you can just like what we did in the last time was to look at second order and see that if you have this kind of crossing lines, this restricts your momentum. And just the same here, you see that here you have this momentum. Okay. Now this means again that we should be able to do an infinite series here. So we should be able, just keeping the relevant class of diagrams, to calculate the correlation function that we're interested in this approximation. Okay. So again, in principle, it's an asymptotic expansion where one shouldn't try to keep all terms in the perturbative expansion, because at some point, if you go to too high order, it doesn't get exact anymore. But again, we're just keeping a subclass of diagrams, so we're fighting this way against this entropic factor, and this allows us to do a complete summation of an infinite series. Okay, and this is what we're going to do here. So first, what we should do is we should translate first here back this into analytic expressions. So let's see actually what we only need to know. So what we have here is we have free propagator P. Okay, so if this is the correlation function which had, like, I don't know, probably I call it K here, it is K plus Q, or K plus Q and K. I don't know how it was called, but you see that this isn't just running through, okay? So we have here just momentum K plus Q and K. So the product of two Green functions, and here it would be K plus Q and K, and then the K prime plus Q prime, okay? So these we can easily attach afterwards, momentum, but then just let's talk about, the weight. So this is coming with a minus U because it's an expansion of e to the minus s interaction, so that's why here there's a minus. The second order now then has a u squared. Then it has a 1/2 faculty from the expansion of the exponential function. But then we have like two ways to insert the interaction vertex here. We can put the one, like we have two, we can put them like this or this. Okay, so this gives another factor of 2. Okay? So in the same way, the third order, we would have a weight of minus u to the 3. Then we have a 3 faculty from the exponential. But then we have like to talk about ordering 3 interaction vertices, how we want to put them. But this is just, the first we can put in 3 places, the remaining in 2 places, so this is just giving us 3 faculty. Okay? And this then goes to just like all orders, no? So in nth order we will have a minus u to the power of n, a 1/n faculty from the exponential, and n faculty because we can put it in every order. So we see that each order comes just with minus u to the power of n. Okay? So this is the weight, and then we can just write now the correlation function that we're interested in the infinite series, okay? Up to here, is it clear or, yeah? So there's one point I leave like for yourself to explore, but it's, you can already see that cross lines will give a restriction to momentum, and the rest is just, putting machinery,
Você fazendo uma coisa perturbativa, seu ponto de referência seria o 0, você não teria.
Pois é, mas quando a gente não sabe o que fazer, a gente faz isso. Vamos fazer. Agora a gente vai ver se acontece alguma coisa que vai sinalizar que está alguma coisa aparecendo aí. Isso a gente vai ver, tá? Isso é... No início você não sabe o que fazer. Então vamos fazer uma perturbation theory em cima do ground state, porque a gente não sabe o que fazer. Isso é tudo para ter uma intuição do problema.
Depois você poderia fazer um set point analysis e também.
Sim, mas aí vai ter um problema. Para set point analysis, você tem que fazer Rabat-Satonovich decoupling. Você vai fazer como? Não sei. Então vamos primeiro tentar ter uma intuição que é relevante para qual seria o canal relevante para fazer a teoria efetiva. Então o passo realmente é sempre, primeiro não tem uma ideia o que fazer, então vamos simplesmente Bom, tem uma coisa que entrou aqui, assim, caiu do seu, que foi, vamos estudar uma spin susceptibility. Isso caiu do seu. Isso vem de alguma coisa. Mas uma vez que você tem isso, você vai ver se aparece alguma coisa interessante ou não. Eu tentei motivar de olhar o spin susceptibility porque, de certa forma, density a gente já explorou. Ainda tem coisas interessantes aí. Pode ter a charge density waves, é uma coisa interessante. Também podemos discutir, mas agora vamos primeiro falar não de coisas feitas que vão quebrar a translation invariance, mas vão quebrar uma outra simetria. E por isso estamos estudando aqui o spin. Mas isso depois a gente vai ver o que vai acontecer. Tá, então vamos aqui só uma vez agora que a gente viu isso, escrever essa correlation function na infinite series. Então o que a gente, so what we said is that the correlation function using the large phase space volume given by like the large Fermi surface gives rise to an approximation which is a ladder approximation which amounts to calculating the kind of correlation function that you're interested in, keeping only these kind of ladder diagrams. Okay, so this is weighted by 1 minus u squared and so on. Now this and so on means just inserting one more like this ladder type of diagrams. So what one can write down is some one can write down this equation in some different form, which I do here now, where one introduces all these higher order terms by some box here, okay? And this box now contains all the information due to the correlations between interactions, okay? So I'll write down in a minute like the definition of the box, but just give it, because this is an important object, I will just give this a name, okay? So the central part in this representation here, like in the last line, the central part of the correlation function is described by what is called a vertex, which here is just a rectangular, and you can give it a name, let's call it gamma. Gamma plus minus corresponding to the C plus minus, which then can be seen to follow the self-consistent equation. Self-consistent equation. Let's first write down the equation in diagrams. So this box should account for all the diagrams that appear here. So if you want to write it, this is given by just a Wiggly interaction line. And then it's given by a Wiggly interaction line, 2, 3, 4, and so on. So we can just, if you want to express this in a self-consistent equation, we can just write this in this form here, no? So this is a self-consistent equation now defining the interaction vertex to infinite order. Okay, so in just iteratively, insert again the lines. Okay, so this represents that all these central building blocks appear here. Okay, you can see. Okay, so this is just rewriting the correlation function in terms of 4 external legs and the central block, which then can be seen to satisfy the self-consistent equation. Okay? Let me just once write down also all the structure. So we have here, in this case, spin up here, spin down here. So spin up here, spin down here. And the external momenta are just the external momenta of the correlation function, no? Because these are the functions that are attached here. So the vertex has incoming momenta here, outgoing here, incoming here, just corresponding to the four legs of the correlation function. So if I copy them from how we introduced them, I think it was k prime plus q. Then there was here a k. Here was a k prime, and here was a k minus q. Okay, so if I write down now the k structure here, well, here it's just, the same. Now here it would be again k prime plus q coming in, a k prime going out, a k going out, and a k minus q coming in. Okay? But now what you have here is, at this vertex, of course, you don't have momentum conservation. So these lines now have a free momentum, and the momentum has to be such that overall momentum is conserved. Okay? So there's some free momentum going in this internal lines, and let me just denote the free momentum here by k double prime, and here k double prime minus q. Okay? So there's some free Green's functions here with k double prime minus q. So you see you have three momenta, and they are so that momentum is conserved. And here actually we have now a sum over this internal momenta, and this is exactly the free sum of a momenta that we said that we want to have per interaction line to guarantee the largeness of this diagram. Okay, so that's why we took the ladder approximation, because here we have the free sum over the Fermi surface k double prime. Okay, so I didn't write it down, but I think we had it like before many times, like the internal lines that appear here. There its internal degree of freedom is just summed over. So here is sum over the internal momentum k double prime. Okay? So this is like the self-consistent equation for the central object that knows about all the correlations. Okay, so that now knows about like the correlations going on here due to the interactions in the system. And this self-consistent equation, this type of self-consistent equation has no name, because this is like, we didn't discuss, like, we are more sticking to examples than discussing like general aspects about perturbation theory, but these kind of self-consistent equations always appear, and they are called the beta-Salpeter equation. Okay? So it's a beta-Salpeter equation. It's like a self-consistent equation for a 4-point correlation function. You probably know like Dyson equation would be the self-consistent equation for a 2-point function. Okay? So in a way, this is a generalization of the self-energy to 4-point correlation function. Okay? This is more or less. Now, this kind of self-consistent equations we already encountered before, actually. If you recall, just a small comment in the discussion of the weakly interacting electron gas, we already encountered self-consistent equation, and there it was the self-consistent equation for the effective photon propagator, so for the effective potential. So if you recall, we said the effective potential can be written in a form where the interaction line, just simply wiggly interaction line, is substituted for by some effective interaction line, which was the sum of the non-interacting line, and then we have here the polarization bubble, and then again the effective line. Okay, so this would correspond to exactly the kind of ring diagrams. Yeah. So this was taking into account like all this kind of ring diagram structures. And so on, okay? This was another example for a self-consistent equation that one typically arrives at after keeping a certain class of diagrams, which then can be summed up to all orders by solving this kind of self-consistent equation, okay? So, in the case of the weakly interacting electron gas, well, we just found from solving the self-consistent equation exactly that the potential is multiplied by the dielectric function. Also, we had the effective potential then, which knew about the screening. So there was entering the dielectric function of the non-interacting electron gas. So here, in the same way, what we can do is we can solve this self-consistent equation, which then allows us to represent the full information in the ladder approximation on the spin correlation in terms of, again, objects that are just non-interacting Green's functions, and which then allow us to look at an expression for the transfer susceptibility, which takes into account infinite order perturbations here, keeping only a certain class of diagrams. So you can actually solve this equation, if you like, diagrammatically, but maybe this is like more how you say, unconventional in the beginning. So let's first translate this in an algebraic equation that we then solve, and then see that we could also just solve this equation diagrammatically. Okay. So let's translate this back. Calling this gamma. This is the product of the Green function. This is an interaction minus u. And what we can do here, in principle, this vertex would depend on k prime, on q, and on k, and spin up and spin down. But let's make the ansatz, and we will see that this is a self-consistent ansatz, so this is fine, that we say that this vertex doesn't depend on k prime and k, so it just depends on the difference here on the small momentum q. Okay? And this we can see here because we'll see we have here free sum over k double prime, so in a way the large momentum k disappears and this only depends on the small momentum q. Okay? So let's make self-consistent ansatz. So if we then translate this equation back into an algebraic form, well, this is on the left-hand side, it's gamma plus minus of q. Then we have here a minus u. And then we have here a minus u. This sum here comes with a factor which is the product of two Green's functions. And then again the gamma. Okay, so structurally this is given by u. Then we have here sum over k double prime, g, k, oh, is it k double prime? K double prime, k double prime is q. And if you want, you can use the spin up and spin down, but this doesn't really matter because this is like the non-interacting Green's function, which doesn't depend on the spin orientation, and then we have gamma plus minus q. And if you recall, so now I don't recall, but I guess there was in fact a T over N, no? When we did the Fourier transform. Yeah? Okay. So there's in fact a T over N. Okay, so this is now the equation that we want to solve. Well, we can just put this here on the side, then factor out the gamma plus minus q. So we have gamma plus minus q times 1 plus the sum here, and then we divide this by the sum and have the solution for gamma plus minus q. Okay? So this is just given by minus u t. Okay? And then we have 1 plus u t. Okay? This is sum prime. But then, I mean, somehow we have here double sum over two Green's functions at k double prime and k double prime minus q. So if we want, we can shift this to plus q. I mean, this doesn't play any role, but just to make it maybe more familiar. So we have the product here, and this is exactly with the free factor t. And what we had before was a volume L to the d. This defined minus the polarization operator. Okay, so I should have stated probably on this. So the n here is the n, which is the number of sides. No? So if you do the Fourier transform in the discrete basis of the CI, yeah. So then you don't have in the Fourier transform a factor 1 over LD to the square root or whatever, but you have for the Fourier transform a factor 1 over square root n. Yeah, for the Fourier transform between momentum and real space. Because you don't have the continuous, but you have defined integers. Okay? So before this was a factor 1 over L to the d, and now here because we have like the discretized problem, there's a pure factor. But then again, so here the product of the two Green's function with the factor t, 1 over LD, which is now n, was minus the polarization operator. Okay? Which we already encountered before, so this can be written as minus u t over n, 1 minus u times the polarization operator is q. Where q is minus t over n, sum over k prime, other prime. Okay. So this is the solution for the vertex. Okay. But let me just state this because sometimes, I mean, so what we did, we translated this back like in formula and then did the calculation. But at some point, I mean, once you have done this once or twice, you can just, instead of like translating back and forth and so on, you can just, I mean, solve this like diagrammatically, you know? So you can write this as if you want 1 minus
não faz diferença, né? Chamar cada duas linhas mais Q e menos Q, é só uma renomeação.
só uma, olha, só queria escrever com mais que aqui porque foi assim que introduzimos antes, mas não faz, só shiftar, né? Não faz diferença se aqui cai o K menos puro. Okay. Então, só para, just to mention it once, so I mean you can go through translating it back and forth between algebraic and diagrammatic expressions, but if you like, you can just also do, I mean, the calculation with diagrams, so you find that this is given by this here. So then you can translate this back in the end, so this would be minus ut over n, this is 1, this is minus, with minus is a plus utn, and then the product of two Green's function, okay? So it's sometimes convenient just to do everything in diagrams and then in the end translate it back. So here, if you like, you can now call this utn, and this here you can also call the polarization operator. Probably minus. Okay. So what we are now, what we still have to do with, let's see. is, so we said, let's look at this correlation function. It might be interesting. We've identified a class of diagrams which should be the most relevant. We are able to sum all these diagrams, so to code the correlation function and vertex function which solve the self-consistent equation, which we are able to solve. So the remaining step, what we have to do is, well, we have to again reconsider this polarization operator. Then, once you have